accelerated exploratory programming, and that will be presented by Jenny Ma. So, take it away.
Hi everyone, really excited to be here. This is my first Kai, so I apologize for the bar.
Woo!
Didn't realize that would happen. But yeah, today I'll be presenting DynEx with, and this work was done with my lovely co-authors who are here today in my lab, and yeah. So everyone wants to develop software with AI, and recently LLMs have had a huge boom with code synthesis and code generation. There are so many code generation apps, including Lovable, Bolt, OpenHands, GPT Pilot, Claude Artifact, just to name a few. And they can generate amazing UIs at an insane speed and offer us a unique opportunity to get ideas off the ground much faster. However, AI also has a specification problem. It can do all of these cool and amazing things, but a lot of times people have trouble articulating exactly what they want and how to do it, and the code generation perhaps isn't harnessed to its full potential. Ultimately, there is a gap in going from an idea to a working solution. Initial ideas oftentimes lack clear boundaries, structured organization, and concrete details. For example, if I'm going to create an application, I need to consider who the target user is, the approach or method that's guiding the solution, and the interaction paradigm or the user experience. All of these elements need to be considered before moving forward with implementation, making the transition from something abstract to something grounded in reality very, very difficult. Thus, our approach is to combine design exploration with implementation to help with AI code synthesis. We present DynEx, an LLM-based approach to code generation. DynEx takes an idea as an input and outputs a functional UI. First, it guides users through a structured design exploration. Next, it iteratively implements the prototype using LLM code synthesis. We created the design matrix, which is an interactive framework for design exploration. The design matrix is rooted in the dimensional design thinking, the dimensional approach to design thinking. Dimensional design thinking is a method of design where it requires the users to think through core dimensions in order to ensure that all aspects are considered. So here are the design matrix columns for DynEx. We have the person, which we need to consider who the application is for and what the goal of the application is. We have the approach, which is the method or theory or strategy that's guiding the solution. And we have the interaction paradigm or the user experience, which could be something like a table, card swipe, newsfeed, or chatbot layout. These are all necessary dimensions that we identified for UI design. Each dimension is then explored on two levels of specificity that make up the rows of the matrix. The first row is the idea, which is a vague phrase that generalizes the design direction for that particular dimension. And the second level is the grounding, which solidifies the foundational details and specifies how each idea needs to be developed. The grounding translates the idea from something into something a lot more tangible and gives the design dimension more color. So in this example of the design matrix, let's say I'm trying to build a language learning app to learn Chinese. In the person dimension, I have something like the beginner visual learner, an expert language learner, or a cultural enthusiast. These are just really short phrases that denote the idea within this entry of person idea. If I select beginner visual learner and then ground that idea, I'll be able to find out why it might be difficult for a visual learner to learn Chinese and like why existing methods maybe don't help this particular group of users. If I move on to the approach dimension, the ideas could be different learning theories like gamified learning, generation and elaboration, or space repetition. And if I select space repetition and then ground that, the grounding will provide a lot more details in regards to how the algorithm should be developed, etc. And then moving on to the interaction dimension, I'll have small ideas of how this information will be presented to the user, like a calendar scheduling layout, a flashcard swipe interface, or a progressive difficulty grid. So this is just an example of the DynEx UI. The user can brainstorm ideas using the system, select them, and then ground them, and then submit each entry in the matrix. And for each entry that you've already submitted, it turns yellow. So the current entry will use these previous entries to inform its current brainstorming in order to ensure that the design is cohesive across all dimensions. The system then takes all the contents of this design matrix to scope the project out. It first identifies the project requirements, which are the technical dependencies that are needed to create an application. In this case, it would be that our visual, language learning app definitely needs images, and it also needs data. And then we generate a spec, which is similar to a design doc. And then we generate data that can be called by an endpoint to serve the prototype. In this case, our data will be Chinese phrases and words that we can use in the prototype. After this, the user can begin implementation in code. We introduce two methods of code generation when implementing our prototype. The first is modular stepwise implementation, and the second one is self-invoking multimodal LLMs. So let's look at modular stepwise implementation first. The system first breaks down the spec into steps and then generates code for each step. The user can also add, remove, and update steps. And the user also needs to test the UI at each step, and they can also debug it before moving on to the next step. By breaking down the spec into components that build on top of each other, we allow for a modularized form of coding, and this also provides a simplified form of version control where the user can revert to a prior working state if needed, because we know that LLMs can sometimes generate faulty code. This is an example of the DynEx UI. So the user can click on whatever step to revisit the working state. They can also toggle between the UI and the code in order to modify the code and test the UI, and they can also debug within each step. So here, for the Chinese language learning app example, we would first generate the code for step 1, which is creating the HTML structure, and then generate the code for step 2, which is to implement the flashcard section, then step 3, the quiz section, and then step 4, the progress section, and then step 5, we would call GPT to generate images, and in step 6, the user can add another step. In this case, it was to add the master words section. Our next idea is in self-invoking multimodal LLMs. So we all know that generative AI is very powerful and versatile, so it makes sense to have our prototypes be able to call it in order to create more diverse and dynamic applications, because this way we can support our apps with data and images on the fly. This can more accurately mimic a user experience, and it's much more powerful than static data. Because of this, we can then create applications such as book recommendation apps, movie recommendation apps, and note sense making apps that dynamically change based on user interaction. So we conducted a user evaluation based on the following research questions. Research question 1 is, to what extent does DynEx enable divergent exploration within a problem space? This is about divergent thinking. Research question 2 is convergent thinking. To what extent does DynEx better allow users to refine or develop their ideas? And research question 3 is, to what extent does DynEx translate the idea into code? And then research question 4 is the general overall prototyping experience. So we conducted the user evaluation with 10 users, and the users used DynEx for 30 minutes and Claude Artifact for 30 minutes. So Claude Artifact is an industry standard tool where you can type in a prompt and generate a UI that is very cool and pretty. So it was a pretty strong baseline. These are some examples of what our users created. We have movie recommendation apps, clothing recs, restaurant recs. We also have this addiction support with CBT. We also have a friend activity sharing app, ticker aggregator, and a rap ghostwriter helper. So the results were that DynEx was able to inspire new solutions and also allowed users to explore a problem space and further develop their ideas. DynEx also enabled users to create more complex and feature-rich applications compared to Claude Artifact. For example, P8 said that after traversing through the design matrix, not a lot of questions were left unanswered. Let's take a look at some more detailed examples. So P6 created a friend activity joining app where DynEx was able to suggest a lot of separate components like matching with friends, visualizing visualizing, friend sharing, joining an experience, and then also sharing experiences with friends. So he thought that it was able to create a pretty robust social ecosystem surrounding the calendar experience and bridge together a lot of distinct UI features that weren't connected at face value. P8 created a concert ticket aggregator app, which was really intuitive and feature-rich. He could sort by different columns, and he liked the conciseness of the information because Claude just presented this sort of basic newsfeed approach that had higher cognitive load that didn't suit his use case as much. So overall, we found that DynEx was able to help users have the minimum amount of human interaction for problem specification. It had relatively low cognitive load, and we found that it can also be applied to domains outside of code generation. So for example, the design matrix as a framework is very malleable. You can add a column easily to add another dimension like stakeholders, and you can also add another row to add another level of specificity to get more of a mental map of your original idea. We also applied the design matrix framework to multi-agent simulations, which is our next research, and found pretty successful results. The takeaways are that overall the design matrix supports recognition over recall and can be applied to a lot of other domains. And as a framework, it is very flexible that allows for easy expansion. And finally, self-invoking generative AI, which is a form of tool calling, creates a lot more realistic prototypes. Thank you, and that's all I have.
So I forgot to mention that this paper actually won an honorable mention award, so congrats. And we'll take one question.